Hello and welcome to day 21 of learning ML from chatgpt. So let's get started. So in yesterday's lesson we learned about clustering, so k-means clustering, it was hierarchical clustering and dimensionality reduction. So in today's lesson I think we're also carrying on from dimensionality reduction and looking at PCA, t-SNE and LDA. So let's see what this is about. So please give me day 21's lesson. Okay, let's see. So next week we've got like the advanced projects, and I can't remember the name of this week's. What was it? Let's see. So we're week 1 introduction, week 2 deepen your understanding, and what was week 3? Advanced topics. Okay. So we've got some final projects in the second one, and fourth one rather. Okay. Day 21, dimensionality reduction techniques. PCA, principal component analysis, a linear method for dimensionality reduction that identifies the directions, principal components, in which the variance of data is maximum. So just to recap what the dimensionality reduction is, we can look back to yesterday's lesson and see that dimensionality reduction techniques like principal component analysis, PCA, reduce the number of features whilst preserving the important structure of the data. Dimensionality reduction can be used, therefore, before clustering to visualize high-dimensional data or improve clustering performance. Okay, so it's basically taking out all the non-necessary ones, so reducing the amount of features. Okay, so a linear method for dimensionality reduction that identifies the directions, principal components in which a variance of data is maximal. t-SNE, a non-linear technique that is well suited for visualizing high-dimensional data in 2D or 3D. It aims to preserve the local structure of the data. LDA, linear discriminant analysis, a method used for both classification and dimensionality reduction, maximizing class separability by finding a linear combination of features that characterizes or separates multiple classes. Okay, so let's start off with a PCA example. I'm also just going to copy this into our Google Colab, and we'll run this whilst we're reading this. Okay, so it's not seeming to. Now please explain the code from the snippets that you have given me. Okay, let's see if we can give a more detailed explanation of the code. Wait, can we switch to O1 in a minute? No, we can't. We try. Okay, let's just see if this one has. Okay, wow. Okay, so we got a lot of data sets here. Load digits. Okay, so it's a digits data set, data target, PCA equals component. So this is all the clusters, and we can see that each cluster is separated via their different color, and we can see PCA component, yeah, and they're all separated into different ones. Okay, so I assume this is similar to the MNIST dataset because it's a digits dataset and it's 0 to 9. Okay, and then we're scattering it and fit transform, and we're reducing the dimensionality to 2. Okay, so this was PCA, which was the linear method for dimensionality reduction that identifies the directions, principal components in which the variance of the data is maximal. Okay, and then now let's move on to t-SNE. T-distributed stochastic neighbor embedding, a non-linear technique that is well suited for visualizing high-dimensional data in 2D or 3D. It aims to preserve the local structure of the data. Okay, let's have a look at this, and let's also paste this in the Google Colab. We'll just read through the code on the Google Colab. Okay, so we're importing the t-SNE dataset. No, low digits dataset rather. The t-SNE. This is the dimensionality reduction model. Okay, so we're doing 2 components like we saw before. So it's in 2D shape and random state. This ensures that it's similar. Okay, we can see that these are much more tightly like clustered together. But we can see we do have a few outliers, like we've got like some blues, light blues over here, which the main cluster is about here. But yeah, okay. So yeah, now let's go on to the next one. To the LDA. So here we're just using the digits dataset and having LDA. It all has the like similar way of doing it. We just do LDA. Well, it's very simple as scikit-learn, as we just do LDA, t-SNE, and PSA. And we can see this is quite similar to the first one. Actually, I mean, it's more spread out the data, but there's a bit of amalgamation just here. But we can see, yeah, just basically the same linear discriminant analysis as LDA. Okay, so now that we've run the code, let's just get a more in-depth explanation of the, I don't know. Let's see. So, assignment. Let's see. Use any of the dimensionality reduction techniques, PSA, t-SNE, on a dataset of your choice. LDA, visualize the reduced data in 2D or 3D and analyze the clustering or separability of the data. Okay, now please explain dimensionality reduction and in very simple terms. Okay, so if we can try and get a better understanding of what it is and just make, like, using like less jargon language. Okay, so dimensionality reduction is a technique used to reduce the number of input features or dimensions in the dataset while retaining as much information as possible. It's particularly useful when dealing with high dimensional data, which can be hard to visualize or process efficiently. There are 2 main types of dimensionality reduction methods, linear and non-linear. Okay, so we're just trying to reduce the number of input features or dimensions. Okay, principal component analysis, what it does. PCA is a linear technique that transforms the data into a new coordinate system. It identifies directions, called principal components, where the data varies the most and projects the data along those directions. How it works. It tries to find the axes or components along which the variance spread of the data is maximized. The first principal component captures the most variance, the second captures the next most, and so on. Simple analogy. Imagine rotating a cloud of points in a 3D space and looking at it from different angles. PCA finds the angle that shows the most spread out view of the points. Ah, okay, that's a good way of looking at it. Okay. So, key takeaway, PCA is useful when you want to reduce the dimensionality of your data, e.g. from 10D to 2D, while keeping most of the information. Okay, yeah. So with that cloud example, for example, it's 3D. We're just compressing it into basically a 2D image, but we're preserving lots of the data as we're looking at it from the most spread out angle. Different angles, most spread out view of the points. Okay. So now we want to look at t-SNE, what it does. t-SNE is a nonlinear method that excels at visualizing high-dimensional data in 2D or 3D. How it works. So instead of focusing on global variance like PCA, t-SNE tries to preserve the local structure of the data. It keeps similar points close together and moves dissimilar points far apart. Simple analogy. Imagine taking a piece of paper with lots of data points marked on it, crumpling it up and then flattening it into a smaller piece without losing the relative distances between neighboring points. But okay, this is it. Yeah, it does consolidate your understanding, but how do you flatten a crumpled piece of paper back into a smaller piece? Okay, but it's a good analogy. So we basically have this thing where it is a dimensionality reduction, but we're just like removing part of the information about it, but we're conserving like the relative distances between the data points. Okay. So okay, and then key takeaway: t-SNE is great for visualizing patterns or clusters in high-dimensional data, but is more about preserving local relationships than overall variance. Okay. So LDA, linear discriminant analysis. What it does, LDA is both a classification algorithm and a dimensionality reduction technique. It finds a linear combination of features that best separates different classes of data. Okay, LDA projects the data onto a line or plane where the classes are as far apart as possible, maximizing the between class variance while minimizing overlap with each class. Simple analogy. Imagine trying to draw a line that separates apples and oranges as far apart as possible in a scatter plot. Okay. Key takeaway: LDA is useful when you want to reduce dimensions while maintaining class separability, making it ideal for supervised learning tasks. So if we go back to this, so it's trying to make them as far apart from each other in order, like to draw a line between them. That was the analogy. When we have a 2D graph separating apples and oranges. Here, if we go back to the t-SNE example, this is where we draw loads of points on paper. We crumpled it up, and then we flattened it out again, whilst conserving the local relationships. So here we have, that's why we see them close together. And finally on the PCA, let's go back to this example. So a cloud of points into a 3D space and looking at it from different angles. PCA finds the angle most spread out via points. Okay, so this is why we see the data pretty spread out. Because, for example, if we had a cloud of the data, which is like 3D, look at it where the data points are most spread out, like we'll have a spread out data set, like we see here with the amalgamation of colors. Okay, so, and yeah, I think that's all for today's lesson. So, thank you for watching, and I'll see you in the next video. Goodbye. Be sure to check in with tomorrow's lesson where we start week 4's lesson. Thank you.